Okay. People can see?
So today we have Jacob Mazor talking about laminations. So let's get started then.
All right, hi. Good to be here. Good to see all of your faces. I would really like this to be as informal as any of you would like. So if you have anything to add or anything to subtract, please feel free to chime in. Although this is, going up on YouTube, so, make sure it's something I would be proud for you to mock me of. So let's start with a very kind of simple question, or maybe it's not a simple question. I don't know. I'm interested in dynamics, so we deal with things changing over time. And one type of thing we might have, one type of situation we might have, is a vector field in the plane or on the sphere or on the real projective plane. These are, don't worry too much if you don't know what S2 or RP2 are, or you don't want to think about them. You can just think about the plane for right now. And we want to know just what happens. This seems like a very typical situation. This happens with water currents. This happens with air currents. Seems like a very natural question to ask. Just what will happen with the dynamics? So we might have some types of points over here, some types of sources, but maybe away from the sinks and the sources, away from these fixed points, what's going to happen? So we might ask about recurrent points. So that means a point which keeps coming back closer and closer to itself. So for example, we might have, right, if we're looking at this picture over here, as it turns out, we're going to have some type of a cycle, actually. I don't know exactly what it's going to look like. But on this vector field over here, we keep flowing around. Some things on the outside are going to limit on this periodic cycle. Some things on the inside are going to limit on this periodic cycle. So that's kind of cool. But can we have, so one type of recurrent point is going to be something which is periodic. So we just keep going in a cycle. Another type of thing, which is maybe we have something else, maybe we don't. Another question is just, unless where can we wind up? We drop a balloon in the middle of the air, it floats around in the wind, and what will happen in the long term? Will it tend towards a specific type of object? Will it trend towards something fractally? So in this picture, again, the only recurrent points here, so everything is going to tend, everything which isn't at this fixed point right at the center is going to tend towards this red periodic cycle. So it's going to keep going around and around and around. And so we have this one type of limiting behavior, which is that everything tends towards a periodic cycle. So any questions about what I just said, or was I using a bunch of dynamics terminology that you didn't know and are too afraid to ask?
What are you talking about?
What am I talking about? Thank you, Tobias. So we have a vector field, and we're just interested, we drop a little point in that vector field, and our little point is going to flow around, and we want to know, can we say anything general about what happens to that point? And I have for you a vector field that I plotted this morning in Mathematica. And in general, that vector, that point is going to tend towards this red cycle over here, this what we call periodic cycle. And we want to know, can anything else happen, or will we always tend towards a single periodic cycle? Or can other behavior happen? So are we all clear on what this question is? Okay.
Starting from any point in the plane, it'll tend towards that red cycle?
With the exception of this one fixed point here, yes. So
okay.
If the vector field is 0 somewhere, then the point won't flow. There's no wind at a point, the balloon won't float around. But except at that one special point. So actually, as it turns out, so I'll translate what this says for you in a second. There's a theorem, which is, I guess, about 100 years old, called the Plunkery-Bendixon theorem. which says if we have a vector field in the plane or on the sphere or on, and I'm going to prove this for you in a second. If we have the vector field, which is, say, on the plane, then any point which continues back close to itself is going to be a periodic point. So we can't have a point which comes back here and then goes around and comes back close and comes back close again and something like that. That's impossible to happen. So I'll draw a better picture in just a second, so I apologize. And furthermore, it's actually true, every single point will tend towards some periodic cycle. So we might have multiple periodic cycles happening, but every point which stays away from the zeros of this vector field will tend towards some periodic cycle. But just to say, it's very important that we're working on the plane or on the sphere. So for example, here's a picture of flows on a vector field on a torus. So it's maybe not clear what's happening. So what is happening? We're taking a point and our vector field is a constant irrational slope. So just to say this is a torus. Well, right? And we have this, so we're gluing together this boundary by identifying the top and the bottom and gluing them together, and by identifying the left and the right and gluing it together. And actually, if we start with any point, it's going to be, as we flow around with this vector field, it's going to be a dense orbit. We're going to have what's called a dense orbit, so it's going to travel just about everywhere. So it's not true that this point tends towards some limiting periodic cycle. It's going to do something much more wild. And so this is just to illustrate that whatever our method of proof of this thing really needs to rely on the fact that we're working in the plane. And it's going to use the main tool it's going to use is what's called the Jordan curve theorem, or the Jordan curve theorem, sorry. And what that says is that every loop in the plane has an inside and an outside, which seems very simple, but that's not true on a torus. We can say, cut one of the pieces of this bagel, and we'll still have a single piece. We won't have two distinct pieces. We'll only have a single region left. But in the plane, we draw a closed curve. We have an inside and an outside. So what's the proof of this theorem?
Jacob?
Oh, yeah. Tim,
can you define what a recurrent orbit is?
Sure.
I know you've sort of described it, but can you
Sure.
like give a more formal definition?
Yes. So a recurrent point it means that, sorry, I'm trying to come up with the best way to describe this. It means that there's a sequence of times so that it limits back on itself, essentially. So we can keep looking at the future in the future. So here's our point P, and here's F1 of P, and here's F2 of P, and it tends towards itself. So as we go into the future, so maybe it goes to other places, but one of its accumulation points as we keep looking into the future is going to be itself. So is that clear to people, or?
Well, one thing that I'm sort of confused on is, you know, you have recurrent orbit and recurrent point. So are you building up to recurrent orbit, or?
Sorry, when I say a recurrent orbit, I mean a recurrent point, maybe. Sorry. That's the same thing. I'll just call that our current point. Sorry. Thank you for catching me on this. should have been checking these slides a little bit more carefully. But thank you. Any other questions before I go and sketch a proof of this? So the first thing is that the second piece of this theorem, just to preface, so can you see my mouse when I'm moving it? Yes, I'm getting a head nod, cool. Oh no, I can't highlight, shoot. This second piece of the theorem follows from the first. So if we have a point whose future doesn't come on, if we have a point and we look at its future, those points need to be recurrent. So you can look at these points it accumulates on, and these points it accumulates on need to be recurrent. So that's so all we really need to do is think about this first part and show that recurrent points, all which aren't fixed, which don't stay in the same place. That's a little bit more complicated than that. I apologize, but essentially we just need to show this first part is what I'm claiming, and maybe we can get a certain sense for what's going on.
Wait, can you remind us what periodic means?
Periodic? That's a great question, thank you. So periodic, in this case, it means that it goes in a topological circle. So it's going to keep going around and around, and there's a sequence of future times where at each future time it passes itself again. So it'll, you know, if your orbit is periodic, you'll keep driving by the same stoplight forever and ever and ever, and you'll keep tracing out the same path forever and ever and ever. Sorry, are we all okay with these things? Are we all?
Wait, so what's the difference between recurrent point and periodic point?
Well, in the plane, there is no difference. But for example, in this picture of the torus,
oh, I see.
We
Recurrent
keep
means
flowing,
it can
it'll
get
be dense.
close it can get close infinitely many times, but
Right, but it'll never return to itself. So if we look over here, it'll keep getting close, but it will never actually return to the same point ever again, actually. So this is, just to say what this is a vector field with irrational slope. I didn't prove any of this, so let's just look at what happens with this proof of this Plunkery-Bendixon theorem, because I think it's cool. So suppose that we have a recurrent point, P, and it's, let's just say we have a recurrent point P and it's not periodic, and we're going to do some contradiction. So nearby, we can take a small little line such that nearby, the vector field is all pointing in one way. We call this a transversal to the vector field. Right, so we take a small little line through this point, and nearby this vector field. So now we start flowing around, and whatever, we do some wild and crazy stuff. We have no idea what's happening here. And eventually, our orbit is going to come back and intersect this transversal somewhere. So let's say over here. It could be on the other side, it's the same type of argument. So are we all clear with what this picture is? So those are point flows. It might do some wild and crazy stuff, but because it's recurrent, it eventually needs to come back close. And if it's not periodic, it's going to come back at a different point of this transversal. But now what happens? We've just gone, so we have this orbit, and we have this little piece of a transversal. That creates an inside and an outside by the Jordan curve theorem. We've created a single closed loop. So what happens with the dynamics on this single closed loop? Well, everywhere on this part of the loop, our vector field is going to be parallel to the curve. It's going to be tangent, except at this little transversal piece where it's all pointing inward. So what does that mean? That would mean, so if we continue on with our path past here, it will never be able to exit our loop to come back and hit that transversal again. So our future time will continue onwards again. It could never come back. Let me use a different color for the future time. It would be stuck inside this inner region.
Wait, why can't it come back?
So how would it come back? It would need to, so again, because we've gone and created a Jordan curve, and it has an inside and an outside. Let's call this inside U. So now after this first return time, if we keep going, our orbit is going to be on the inside. It's going to be inside U. And in order to escape, that orbit would then need to either cross itself, which it can't do. And that's really the only thing that can happen. Or it would need to come back, I suppose, and cross over here. But it can't cross backwards over here. Remember, these are all have direction because our vector field is pointing up right over here. Is this clear?
Can I add something?
Yes, absolutely. Please add something.
So I think implicitly in a lot of this, we're assuming, and you may have mentioned this already, but we're assuming that this vector field is continuous, and that's sort of needed
so it's
for us to like not cross, right?
Vector field, right? So it can't cross itself. I apologize. I'm like just assuming everything is completely smooth, and I'm not worrying or thinking about that throughout this whole talk.
And that's also why we have the transversal, right? Because it's smooth.
That's also why we have the transversal, yes. So this is an important thing to think about. I'm just trying to give you kind of a sketch of what these ideas are. So the point is that any recurrent point, which sort of right, any recurrent point which isn't fixed actually has to be periodic. So are we all happy with this, or we hate this? I'm just trying to give a motivation for what these laminations are. I haven't even used the word lamination or defined it or anything yet. But I would just like to say, what we've gone and done is, in some sense, we've divided up the plane into little regions, which look like these tangential pieces, which are going along the vector field. And then we use this transversal. So the question is, can we try and generalize this topological picture we have using these vector fields? And the answer is yes, and we're going to use something called a lamination to go and look at how this happens. So what's the idea? So a lamination is kind of like a manifold in the sense that it's a topological space. And we define it using local charts. Right, so the definition of a manifold, or of a smooth manifold, let me say it's of a smooth manifold, is we can cover each piece of our manifold by something which is locally Euclidean, and then these charts need to satisfy some type of compatibility condition. So these transition functions need to be smooth, et cetera, et cetera. So what's a lamination? A lamination doesn't look like a single Euclidean space. What we do is we cover it by these, I think of it like a stack of sheets of paper. So each region of our lamination, we can cover by a stack of sheets of paper. So it's sort of smooth in this direction. So it's got like a nice smooth manifold type structure in this horizontal direction, like a sheet of paper. And then up and down, we only have continuity, right? So we need to specify that it needs to be somehow like continuous up and down, because this up and down space, it might only be, say, a Cantor set, or, you know, I don't know, just some topological space. It might be, itself it might be smooth. It might be smooth, but we're not using any type of smooth structure. So the kind of idea, so to give us a real thought of what's happening, is we're allowed to move along a single layer, and things need to look manifold-like on that single layer. Things need to look smooth. Things need to look, you know, as nice as they can. But up and down, we can't move our paths. We shouldn't be moving any type of path across layers. We shouldn't even be thinking of these layers as having any type of structure beyond being continuous. So maybe we have some type of metric on the transverse. So this is called, we call these pieces leafs. And let me use a different color. This vertical direction, this is the transverse direction. So I'll say that things in the leafwise direction are smooth, things in the transverse direction are just continuous. Right, we also need to have some type of overlap condition between these charts. I said we can cover each open set of our lamination by this stack of paper. But then we need that when they overlap, that sheets of paper go to other sheets of paper. So they can't overlap. We can't have one sheet of paper intersecting a few sheets of paper. It needs to be, right, each, if we look at this piece, then in each of these charts, a sheet of paper is only going to a different sheet of paper. Okay, I got at least one head nod. I'm saying sheets of paper. I don't know if this is a good analogy for people to be thinking about, or this is just, people have no concept what I'm saying and they're already bored and confused.
Do we think of each leaf as the same? Like, are they diffeomorphic or something?
That will be.
Or can they be different?
Oh, so that's a good question. So, in general, right? So there's this concept of these local leafs. So those are usually called plaques. Versus we can start piecing together. Now that we have these charts, we can piece together all of the pieces which come. You know, we can go from one sheet of paper to another sheet of paper and a different chart to another sheet of paper and a different chart and take like a union of all of these.
Right, sorry, I just meant in the chart.
Right, so in that chart, they will all be the same. So in this chart, each chart, I should really just say, this looks like some n-dimensional ball times a transverse space. So it's really just each chart is a product. Right, so that kind of gets to a very interesting point, which is that we might stay on one leaf and then, you know, go around into different charts and different charts and different charts and different charts and different charts, etc. And we might come back onto a different leaf in the same chart, or what looks like a different leaf according to this same chart. So we go around and we come back somewhere different. And we'll talk a little bit more about what that is. That's called holonomy. There is a chat question. Is the dense orbit of the torus you drew an example of a lamination? Yes. So in fact, so there's a question in the chat, is this orbit plot, or is this streamline plot, or whatever you want to call it, an example of a lamination? The answer is yes. In fact, any vector field gives you a lamination. We're going to see that in a second with one-dimensional leaves. So this is a very interesting and good example of what happens because, right, locally, this just looks like an interval times another interval. We can put this into charts where it just looks like one interval times another interval. But globally, what's happening is that we're getting an embedding of R, which is a non-compact set, or non-compact space, into the torus, which is a compact space. So we need to deal with the fact that we have something which is essentially infinite. So R is somehow this essentially infinite thing. It has, infinite length that we're throwing into something which is kind of finite. And this is giving us some type of structure which is seemingly pathological. So we've got this type of structure which it looks very dense. And this is about as nice. For things which are pathological, this is actually very nice because it looks the same everywhere maybe, but
is the transverse data for your lamination chart fixed?
Is the transverse fixed?
Like, does it vary from chart to chart, or is there one fixed model?
Sorry, I'm trying to think. That's a very good question. I don't think it makes a difference, actually, but for the time being, let's assume that there's one fixed model.
And do you require compatibility for the transverse data also when you glue them together?
Require compatibility for transverse data. So yes, so what needs to happen is that, right, one transverse slice, so right, we have one little chart might look like this blue thing, and a yellow chart might look like this thing, and we need to go, ooh, that was bad, hang on. Our leaves need, our sheets of paper need to agree. So a sheet of paper can only intersect a single other sheet of paper. It can't intersect, or maybe it doesn't intersect any sheets of paper, right? So they don't, these two charts over here, they don't match up along the whole transversal. They just match up along a certain open set on it. Okay, I'm getting a head nod from you, so that's good. What else is happening? So we want these, right? We've got these charts, and we can talk about transition functions on each leaf. So on each leaf, we need a smooth transition on this overlap. And we need all of those derivatives to be continuous in the transverse direction, in this vertical direction. So again, this is kind of the philosophy that we have manifold type things happening in this horizontal direction, in this leaf-wise direction. Oh, another one bites the dust with Tobias. And then all of this smooth stuff needs to change continuously in this vertical direction between leaves.
Jacob, I have a question.
Yeah, please.
How do we distinguish between what is vertical and what is horizontal on a topological space?
That's a great question. So it's distinguished by the charts themselves. So I've been drawing these pictures very suggestively, but our charts themselves need to come with a distinguished horizontal direction and a distinguished vertical direction. So thank you, that's a very good question.
Okay, thank you.
No. So I'm glad that was, I'm trying to decide if there's anything else I want to show you right now, or if let's move on to some examples. And you guys can tell me to head on back.
Can I ask? So
Oh,
what
please.
if you have an unstable limit cycle, right? Can you then still make a lamination, right? Because at one side the flow is going one way and the other side the flow is going the other way. That doesn't change anything.
Sorry, what do you mean by unstable limit set?
So in the first picture, no, unstable limit cycle. So in the first picture, you drew a stable limit cycle.
Yes.
Yeah, the flow is kind of going towards the limit cycle.
Right.
So now I'm asking, well, it could be an
Oh,
unstable
what if it's all
limit
going
cycle.
away from the limit cycle?
Yeah, does that like influence your lamination at all?
I mean, so let's just say we reverse all of the arrows in this picture. So everything is
Exactly,
going
yeah.
in the opposite direction. So we still have a lamination of our whole plane, right? Our whole, or minus this one singular point where we have no vector field there. Our vector field is 0 right at the origin, but other than there, we still have a lamination of our whole plane. We've maybe just given, we can maybe orient this lamination and give it an opposite orientation, but you know, still at every single, right, we take a little, we still divide up our
Yeah, okay, I see.
boxes into, right, so in this case, right, again, our boxes are distinguished. So actually what I've been calling our horizontal direction, our leafwise direction, is in this box vertical. So maybe vertical and horizontal are bad words because they kind of suppose you're looking at this from a certain direction. But I find it helps me a lot when thinking about this to give our charts certain consistent orientation so that our leaves are happening horizontally, our transverse stuff, which might be very bad, is happening vertically. I hope I got those things.
Sorry, Jacob. In that example, would both cases with arrows one way or the other give the same lamination?
Right, so now that's a good question also. Now that we have these types of objects, so I would say yes, but now that we have these types of objects, we can start putting more structure onto them. So if we have a one-dimensional laminate, so a lamination with one-dimensional leaves, then we can start asking about oriented lamination. So we might say an oriented lamination is a lamination where we've also picked a direction along the leaves. Or we can start talking about geometric structures on these things, because now that we have smoothness in this leafwise direction, we can talk about, right, so maybe not everyone knows this stuff, but we can start putting tensors and metrics and all sorts of things. And again, we require things to be smooth in our, what I'm calling the horizontal direction, in our leafwise direction. And all that smooth stuff needs to change continuously in our transverse direction, in what might be much more pathological. Okay, so, right, so every vector field gives us a lamination, right? And I should just say, we've only looked at things with one-dimensional leaves, but we're gonna look at things with bigger dimensional leaves in just a second. So these horizontal directions don't need to be one-dimensional, they can be n-dimensional, whatever your favorite n is. So every vector field gives a one-dimensional lamination by just looking at these flow lines. So maybe we can even orient those if you want. So if we embed it and we're away from zeros, then, and now we can ask, well, what if we have like 3 vector fields in a 4-dimensional manifold? When does that give us a lamination? And if you remember that one theorem, the Frobenius theorem from differential topology that you learned just for comps, that's what it says, is it says, let's say we're looking at 2 vector fields, x and y, in a 3-dimensional manifold. So x, y are vector fields in M3. They form a lamination with 2-dimensional leaves. Oh, hang on, I've got a question from the chat. How does a lamination differ from a foliation? Okay, I will answer that in just a second, Jacob. So, right, these 2 vector fields will form a lamination if their commutator, whatever that is, if you know what it is, great. If you don't worry about it, lies in the span of these 2 vector fields. So there's a question, there's a very related concept called a foliation. versus a lamination. It's too many Asians. And the difference is that I'm not assuming that my total space, so a foliation is a lamination where somehow you're filling up a whole manifold. So for example, you have this local structure and you're covering the whole manifold with this local product structure by these charts, which are, products of spaces. And meanwhile, lamination, so maybe we have some singularities for our vector field, and we don't want to define this structure, this product structure everywhere, so we only define it in certain places, or we don't even define this on a manifold. We might define it more abstractly, and that's what the difference is. I hope that answers your question. Okay, am I still with people? Or are we totally zonked out? Okay, I'm getting a thumbs up, so that's good. Thank you, Owen. So now we can restate our little theorem here. So we have this thing about limit cycles, etc. And I don't. We can say that, so a minimal lamination means that we can't throw away leaves and still get a lamination or a closed one. Somehow it's the smallest compact thing, which is still contains leaves, still contains complete leaves. So if we restate our Plunkery-Bendixon theorem in terms of laminations, we can say that every minimal lamination in S2 reduces to a circle, which means the exact same thing that I said before. It's the same picture that orbits or the future, they all need to limit on circles. Wait, what are you looking at? Willie is blinking. Willie is unconvinced.
What do you mean by reduce?
What do I mean by reduce? So I guess in this case, I mean is a circle. But, right, so what does it mean for it to be a, that's a good question. It means I was very tired when I was writing these slides.
Each leaf is a circle?
I'm sorry, what? So not each, so is just a circle. So not even each leaf is a circle, because that wouldn't be minimal. So, right, so let me, right, you could think of a lamination where each leaf is a circle. And we want to say, does this have any compact subsets, which are the union of leaves, right? So we don't want to think of taking a piece of a leaf when we're looking at a lamination. We want to look at the full union of leaves. And the answer is that this does, a single circle is itself a minimal set, because it is the union of leaves, it is the union of itself, and it is compact. Meanwhile, the torus does have minimal lamination. So let's go back up here, because every compact subset of the torus, which contains a full leaf of this, is the whole torus. I'm getting blinks. Am I going too fast? Are people good with the speed, or am I? It's easy to think that you're not going fast enough when in reality you're just buzzing through things. So, okay.
I'm still a bit unclear about what we mean by the lamination reducing to a circle. I can understand leaves being circles on the sphere.
Right, so what it means is that if a minimal lamination means that we can't, so yeah, don't worry about this reduces to, because I'm just being up in my head, I'm sorry. The question is, we have a lamination, do we have a sublamination? Do we have something which is essentially a smaller lamination? And the answer is, if this is the case, so aren't a point and S2 both minimal lamination? So I should say every minimal one-dimensional. So minimal lamination with 1D leaves. So thank you, yes. You should specify the dimensions of your things also. So what I mean is, if you have a compact lamination in S2, which is not just a circle, you can always find, but yeah, you can always find a circle inside of it. So you somehow can't, right? That's what we proved with this Plunkery-Bendixon theorem, is essentially what it is. I should also, I went a little bit fast here. If we have a lamination, which is in the plane or in 3 space and has one-dimensional leaves, we can find a vector field that goes with that by just taking a tangent at each point, a tangent vector at each point. And maybe we need to figure out how to make this smooth. So maybe that's a little bit harder than what I just said. So if we have a lamination, then we have a vector field, and we can use this earlier, dynamical version of the Plunkery-Bendixon theorem. Anyways, we can't write the sphere as a union of circles. And so what this means is that each vector field on the sphere has to have at least 1 0. Because if not, then we would be able to write the sphere as a union of annuli, essentially. Okay.
Jacob,
Yes.
is that basically the Hairy-Ball theorem?
Yes, that is the Hairy-Ball theorem. So this is a different proof of that theorem. But it's maybe worse than the other proofs. The other proofs tend to be much more powerful and give proofs for other types of, this only works for S2. This doesn't work for any other manifolds. Versus other proofs can work on other surfaces and can work on higher dimensional spheres, etc. This only works on S2, but I think it's a nice consequence. Anyways, I'd like to show you some cool pictures, at least for a little bit. We've got, what, a little bit more than, that's not a great picture. Here's a nice picture. So let me show you examples where not all of our leaves are diffeomorphic. So let's start. So I drew some curves on here, and let's rotate everything. So we're going to imagine rotating all of this around this axis in the middle. And then because we have this, so each of our leaves looks like this kind of cupped, it looks like an infinitely long solo cup that's all stacked inside of this sleeve. And it's all happening periodically, so we can go and we can fold our big long sleeve into a torus. So remember, our whole thing is happening as a circle. So this is what this picture shows. And you should picture that this is all happening, sitting here, right? So this is a lamination or a foliation of the solid torus, as they say. And it's all sitting inside here of 3-dimensional space. Now, as it turns out, so this is, you all kind of look a little bit confused or maybe bored. But now,
oh, Jacob?
Yeah.
Is the boundary somehow included?
Is the yes, so the boundary is also included.
Okay.
So we're including this boundary. However, what we're going to do is we're actually going to, so if we're looking actually, so we now add some point at infinity and we get the 3-dimensional sphere. It might be hard to picture, but if you take the 3-dimensional sphere and you pull away a solid torus, you're left with a solid torus. So you can picture, one way to picture that is, right, there's going to be a line coming through this solid torus, and that's going to connect all the way at the ends at infinity. That's happening in this complement. And that kind of gives you a way of picturing what the other kind of main meridian of your outside bagel is. So if you take a sphere and you pull, or a 3-dimensional sphere and you pull away a bagel, you get, and now we can start going and doing the same type of foliation of the outside using these, you know, wrapped solo cups. So this is gonna, I guess, come in and spiral around. Let me, uh-oh. There we go. Right, so a single leaf is gonna come here and it's gonna go and spiral around and come back, etc. And it's gonna close in on this other direction. So this is maybe very, I don't know if it's very interesting, but we've gone and we've taken a lamination, which the whole thing is equal to S3. And somehow everything accumulates on this single torus that's sitting in the center of this lamination somehow. I don't know, this is an interesting example. It gives lots of counterexamples to some very basic questions you might ask, like, can we, if we have a lamination, do we have some sort of notion of a universal cover? So that's a type of question you might ask if you're used to, you know, manifolds. Manifolds have universal covers. Could laminations have universal covers? And the answer is no, because we have no good way of forming a cover of this type of object, at least in the standard way. All right. Here's another pretty picture. So what we can do is we can take, I can talk about these other things, but they're more technical, and I've come back from an hour of teaching anyways, and we don't even have that much time left. So here's a picture. We can take a torus and we squeeze it and double it, and then keep repeating that and keep repeating that and keep repeating that. And we eventually get, so let me draw a cross section of what happens. So a single torus, we squeeze it and we double it and we put it inside it. So this is like the first cross section. And then we take a cross section of that and we're going to intersect it in these two places. And then we take our next iteration, we intersect in these two places. And we keep squeezing and squeezing, and eventually each cross section, so any cross section intersects in a Cantor set. So this is something that looks sort of like it should be a circle, because we have these one-dimensional, right? And you can check that each of these resulting pieces we get, because we keep shrinking and shrinking and shrinking, is just one-dimensional. So this is a lamination with one-dimensional leaves, and its transverse is a Cantor set. And it looks like it should be similar to a torus. This is called a solenoid. Or sorry, not a torus. It looks like it should be similar to a circle. However, this space is not, it's connected, but it's not path connected. And the reason it's not path connected is because if I wanted to get from one point to another point, I would need to come and cross this transversal uncountably many times in general. And you can't do that with a, you know, a path of finite length or even sort of regular infinite length. I don't really know anything about logic or topology, so, you know, it needs to be a very long, in order to, this is maybe a technical thing. In order to get from one point to another, you'd need a very long path, or like a path from the very, a continuous image of the very long line, whatever that is. But right, in general, we can't do that with a single. So this is connected. It's not path connected. So that's kind of interesting, maybe. This was a cool image that Karina shared. Or something similar. So one other way that laminations come about in people's thoughts is you take a circle and you start identifying points. And then we're just going to draw circular arcs that connect those identified points. So for example, this point and this point and this point, we're going to identify all three of them. So we just start drawing all of these three circular arcs between them. And then we can ask, what happens if we collapse all of these identified points? So any points which we identify, we just collapse those together. And we can get some very cool fractals. So this is called the Duodee rabbit. It comes up in complex dynamics. And it has a model based on this lamination of the disk. So so I'm only drawing a few of these lines, but in general, somehow there's lots of stuff happening inside these seemingly empty looking disks. So you should sort of picture these things as being filled in. Oh, there's a question. How do you choose which 3 points to identify together? So you're given an identification on the circle, and then you start drawing the lines that connect these identified points. So there's some other process that gives you this identification usually, and then you just start drawing these. And so this lamination on a circle, which is a very cool picture, gives you some type of model for this fractal in some way. So there's a postdoc here, Peter Lin, who looks at what happens if you sort of randomly assign a lamination to a disk. And he's done work on that, and it's cool stuff. You get cool fractals. Here's another kind of thing that I think is cool. So you can specify a lamination as opposed to, putting it inside of something else. We can try to simply define what our leaves are and make a lamination out of this. So what are our leaves? So this is called a Penrose tiling. So we take two types of rhombi. So these are rhombi. So I think it's out of 5. So that looks right. So you have our fat rhombus, which is angles 2 pi over 3, 2 pi over 5, and 3 pi over 5. And we have our skinny rhombus that does not look like a rhombus, which is pi over 5 and 4 pi over 5. And these will tile the plane, but they'll do so what's called aperiodically. So you won't have the same, you might have the same pattern repeating itself, locally. So we see that this little tile over here repeats itself over here. The tiling is found on the ground outside the Simon Center. So you can go and look and play around with it. And sort of every finite combination you can have is going to occur in any single tiling. So if we zoom out, we might see, we keep repeating this tiling somehow. We might see this pattern again, but it won't come regularly. It will all be somewhat. So now what we can do is we define each leaf, we define a lamination, and I guess you need to show that this actually makes sense, where each leaf is a different tiling of the plane, and 2 leaves are close. So say they're close at this point if they agree for a long amount of time. And this is another way, so maybe it's completely unclear what you do, but you can, just by specifying combinatorial data on your leaves, you can go and define a lamination in this way, not just by taking, not just by looking at in these other ways, we kind of had an existing space where on which we defined our lamination. And this is a different type of way that we can do things. We start with what we want our leaves to be, and we can define how to move between them transversely when our two leaves close, and this will define a lamination for us. And it's really unclear in what way this thing is going to be folded up. All right, well, there's about 5 minutes left. Here's another cool picture. I am happy to sit around and talk for another 20 minutes or something, but I don't think I have enough time to finish up what I wanted to say anyway, so we can call it quits here. And thank you all for coming.
Thank you.
Thank you.
Yeah, any questions or what questions?
Yeah, I have a question. Could you go back to the previous picture?
This one.
Yeah. So I didn't understand what you said about making the lamination. So are your leaves just like R2?
Yeah, so your leaves are R2. Or they're R2 plus a tiling. And then you say that two leaves are close when they agree. So I guess there are two with an origin. You need to specify an origin point. Right, so there's a different.
How do you like remember the tiling? Because you said it was like smooth in the leaf direction.
Right.
So, like, what does it mean to remember the tiling?
That's a good point. So what's a tiling? A tiling is like a set of marked points, right? So it's just certain data on your leaf direction. So
it's like a lattice or something?
Yeah, I guess it's like a lattice. Right, so what do we... Right, so it's a graph on an R2. So I guess that's what our it's R2 together with a graph embedded on R2 and a specified point at the origin. And then we say, you know,
then you use the, yeah, okay.
Yeah, we use the graph to say when two leaves are close.
Okay, I see, that makes sense.
Yeah, but we get something like very wild when we construct this. It's really maybe, I think that it's related to something from like a projection from 5 dimensions to something else or something, but I didn't understand it when I was looking at this. I just think
Can I
it's...
ask another question?
Yeah, please.
Is there like a notion of dimension for these laminations?
Yes, well...
Do you just define it based on the dimension of the leaves?
Yeah, so that's really the only thing you can do is define it based on the dimension of your leaves, which, right,
There's
it makes
no like fractional dimensions you can make sense of in the other direction?
So...
Like for the Cantor sets, is there like a notion of dimension for that? I can't remember.
There is a notion, so there's a notion of Hausdorff dimension, but that's not a topological thing. That's based on how you're embedded, right? Cantor sets can have any dimension from 0 to the dimension of the space that they're in, I think. So, or at least say in R, they can have anything from 0 to 1, inclusive on both sides. So it would depend on how you're embedded into some bigger space, I suppose.
Thanks.
Yeah, other questions?
I was wondering, so if you have a 2-dimensional leaf, will that always have like 4 sides to it?
So what do you mean by that?
I guess like it looks like a square when you draw it, or like the like sheets of paper.
Oh, right. So let me try and draw what might look like. Right. So this might look like your 2-dimensional chart. Right, so I'm drawing it with these papers like this. Sorry, I'm like not sure if I'm drawing this well at all and you can see what's happening or you can't see what's happening. Yeah, drawing is hard. Maybe it'll work better if I do it up here. Yes, yes, it did. Right, so we have our intersection over here. Right, so these are open two-dimensional sets. They'll topologically be balls or squares, which are the same thing. Sorry, I don't know if that makes sense. I don't know if any of this made sense, but yeah. So did that answer your question or just make it more confusing?
Yeah, I guess I was just still thinking about like the notions of like sides and top sides, I guess. Like, do we always have like matching pairs of those?
No. So on each leaf, they're just going to intersect in open set. So they won't necessarily match up sides to sides or boundaries to boundaries or anything. We'll just kind of intersect.
You could probably think of a 2D leaf as a disk, right?
Yes.
Instead of the square.
Yeah, sure. That works also.
I see. Okay, thank you.
Yeah, sorry, I didn't get to say at all why these things are important, but they're pretty sometimes. This is pretty. This is a pretty picture.
And you can also have leaves that are like infinite dimensional, right?
You could. You would need to figure out how to best work with that. I'm kind of scared of that. But yes, you could have leaves that are infinite dimensional. So,
I'm thinking on like the space of quadratic like maps.
right. So
But
I
that's
think what happens a lot in math is that an object is used or introduced and works out kind of well, and then everyone in that field likes to use that same type of object to define other things. So these things are very big for geometric topologists because of Bill Thurston did a lot with them. And they're big in complex dynamics, I think also because Bill Thurston did a lot with them. And other things. So you have models for different types of complex dynamical systems where the space of these maps is given by a lamination with infinite dimensional leaves. Yeah. I don't know. All right. I'll stick around for a while. But this was a full hour, yeah? Yeah.
Yeah, I guess we can stop recording now. But...